Hello and welcome to our August edition of the Virtual Java User Group. For those of you who don't know me, my name is Sam Heppen and I'm one of the Virtual Drag organizers. We're a global community bringing you high quality tech talks and speakers from all around the world. I think today's speaker is calling in from Singapore, so definitely all around the world. And myself and Grace are based in London, so definitely a global community. So thank you so much for joining us. I've already seen some comments in the chat, but I'd love to know where you are all calling in from. I think we've got someone from Peru, from Bosnia, we've got Ottawa, we've got the Netherlands. So welcome everyone. Please keep adding in the comments where you are watching from. I think my line's a bit staticky, Simon. Hopefully, I did just charge my AirPods. Let's see how that goes. But today's session will be hosted by Java champion Grace Robinson. Grace is a product manager at IBM working with open source Java and cloud technologies. She'll be joined by Haoyi, an MIT grad, open source powerhouse with over 10,000 GitHub stars. Wow. And a JVM expert who has built infrastructure at Dropbox and Databricks. So before I bring them up on stage, if you do have any questions for our speaker today, please pop them in the chat. It's exactly where you're sharing, where you're phoning from, or where you're watching us from. And Grace will get them over to Haoyi at the end of his session. If you're watching this post live, so you're watching this on replay on YouTube, if you join our Slack community, I'll get that up on screen now. But if you enjoy the VJug Slack, you can ask both Haoyi and any of our past speakers any questions, and they'll be able to answer those, as well as join, I think, over 20,000 other Java community members in that group, chatting about all things Java. But that is enough from me. Actually, it's not enough from me. You get to have one more thing from me. We are actually raffling off a ticket to Dev2 Next. So if any of you are really keen to go to Colorado Springs, or if you're based in Colorado Springs, they're running a conference from September 29th to October 2nd. And we have a free tickets to Dev2 Next. So if you want to go to this URL, which I'll also drop in the chat, let's do that quickly. Pop that in the YouTube chat so it's easy to click on. But if you go across to that and enter in on Friday, we will be announcing winners. So if you're keen to join us at Dev2 Next, please do that. But now that is definitely enough from me. So let's bring Grace and Haoyi on stage. Hello.
Hello, hello.
Hello.
Amazing. So much, Grace, you're in London with me, right?
I am indeed, yeah. So it's not quite dark here, but I think it is with Haoyi.
Yep. That's the window out there.
Perfect.
Yeah, it's great
Grace, I'm going to hand over to you. But again, anyone watching, please pop those questions in the chat, and Grace will be able to get it to Haoyi during the session.
Absolutely. Thanks so much, Sam. Appreciate it. It's so great to be back here with the Java community. I know some people on the chat, so hi. If I've met you before, hi if I haven't. Thank you so much for giving up your time and joining us today for this virtual session. And Haoyi, we're going to have you presenting about simpler Java build tooling with object-oriented programming. I'm super intrigued, having only used build tools like Maven or Gradle. I'm really intrigued to see how, there's performance improvements that are going to be gained from this and other benefits. So, yeah, really excited. Please take it away.
Okay. Okay, you guys can see the screen now. Great. So hi, everyone. As Grace mentioned, this presentation is about Java build tooling. So the motivation for this talk is that although Java as a language is known to be extremely easy to learn, very performant, and have great IDE support, Java build tools like Maven or Gradle don't always live up to that expectation. And this is not just a Java problem, this extends beyond Java. You go to JavaScript, you go to Python, and build tools are always kind of a long-standing pain point and frustration throughout the programming ecosystem at large. So this presentation, we'll have 4 sections. We'll talk about why are build tools hard from a user perspective, like as a person just trying to build your application, what are the challenges you have? But also why are build tools hard for implementers? Like Why isn't it so hard for someone to just make a better build tool for Java, for Python, for JavaScript, or something else? We'll talk about Mill, one of my open source projects that aims to be a better build tool. We'll talk about some of the improvements we've been able to demonstrate. And lastly, we'll talk about this idea of object-oriented builds, where we're able to use these core concepts from object-oriented programming to like dramatically simplify these build tools, taking something that's previously really complicated and confusing and make it something that's really familiar and easy for anyone who's learned Java 101 to pick up. So first, about myself a bit. So I learned Java in 2004. This was more than 20 years ago now, and I've been working on various open source projects as a on the side since about 2012. My last job was at Databricks. Databricks is a Scala shop, so many of the side projects are Scala on the JVM, but also many other Java-related or other JVM technologies involved. So my professional work is developer tools. So basically everything that happens before your code goes to production, dev environment, CI systems, testing systems, and build systems, which is the topic of this presentation. I'm currently on sabbatical, so spending my time working on these open source projects to try and see if people like them. So the first topic we'll talk about is why are build tools hard for users? And from my experience using build tools in Java and other ecosystems, this largely boils down to 3 bullet points, which we'll go through in turn. The first bullet point is performance. So everyone talks about how Go compiles very quickly, for example. Very few people out in the world talk about how Java compiles very quickly. And in one side, that's not that surprising. Like if I take as an example the Netty code base, Netty is an open source asynchronous networking framework. It's a medium to large project, 500,000 lines of code. It takes about 50 seconds to compile using 10 cores on my laptop. So this is without testing, without linting, without all that. Just compilation takes about 50 seconds. So I'm going to kick this off in the background so you can see. So I have my terminal here. I'm just going to go to my Netty project and go run this. I'm not going to make you wait for the 50 seconds. We'll come back later. But this doesn't seem very quick, right? Like people talk about Go compiling instantly. When you snap your fingers, by the time you press enter, it's done. So if you look at Netty, 50 seconds is a while. If you look at a single module within Netty, like Netty Common, that's about 29,000 lines of code rather than 500,000. Takes about 4.5 seconds to compile rather than 50 seconds. In this case, I'm using compile versus install, but it doesn't really matter here. And we're looking at more or less the same speed at compilation. So 4.5 seconds to compile a single module is okay. It doesn't feel particularly fast or slow. It's okay. And that's why people don't say Java compiles quickly. But what people usually don't realize is that if you just take the Java C command that Maven prints out and that is running, and you run that command yourself, it actually is a lot faster than running it through Maven. Instead of 4.5 seconds, it takes 1.5 seconds. So there's a lot of overhead here that your build tool like Maven is adding to what's actually a relatively fast underlying Java compiler. And those of you who are experienced Java developers will know that running Java C like this cold from the command line is the slowest, worst possible performance you could get out of the Java compiler. So that's because Java C is a Java application running on the JVM, and the JVM is known to have a slow, cold start, but gets really fast later when it warms up. And by running Java C as a command line application like this, you always just get the cold start and it never gets a chance to get warm. And it's already 3 times faster than compiling it using Maven. So if you actually run Java C warm, which I have done in the benchmark here, I'll show you in a moment the code for this, you'll see that it actually takes 0.3 seconds to compile the same 29,000 lines of code with the same dependencies and that same Java compiler even, rather than taking 4.5 seconds to compile using Maven. We're looking at the 15x speed up purely by just taking away the build tool and keeping a JVM warm, which is like Java JVM Ops 101. Everyone knows you should keep the JVM warm to get good performance, right? And by doing that, you're already 15 times faster than Maven. So just to show this to you live, early on we kicked off the Java compile in the terminal. You guys hopefully can see here. It took about 58 seconds, about 50-something seconds, like what we saw on the slide. If I run the Maven compile for a single module, which I'll do now, it should take about 4.5 seconds. This is a clean compile of the Maven, of the Netty Common sub-project within the Netty code base using Maven. So yeah, it took about 4.5 seconds. If I then run the Java C command that basically does the same thing, you can get Maven to print this out and just paste in the terminal. You'll see it takes less than 1.5 seconds instead of 4.5 seconds. And lastly, if you run this bench.java file, which I'll show you in a moment. So bench.java, let me pull it up. It's just a small single file Java application I wrote. And all it does is there's a while loop that calls a Java compiler in memory over and over. So it's literally doing the same thing as Java C, but we give it a chance to get warm rather than just benchmarking the cold worst case performance. So if I run this from the command line, you'll see the first time you run it is not particularly fast. It takes some time to run. But as it runs over and over, you see this duration here getting shorter and shorter. And this is, as you know, the Java compiler gets warm, the Java virtual machine gets warm, and that's the Java compiler running on top of it. So that gets sped up. The method calls get optimized, it gets JIT compiled to fast inline assembly. And within not too many runs, we're looking at around 300 milliseconds, or what we saw on the slide is 0.3 seconds, to compile 29,000 lines of code at about 100,000 lines a second. So when people say things like, oh, Go compiles quickly and Java always feels a bit sluggish, they're talking about the Java experience you see up here, where compiling a single module takes 4.5 seconds. But you're not talking about the Java underlying infrastructure, which actually is a lot faster than that, 15 times faster. And if I would guess that if people found that Java modules compiling in 0.3 seconds, literally you press a button before you blink it's done, they would think Java is a very fast tool chain and fast language. But because the tool chain of the build tools around it add so much overhead, Java then gets reputation for being kind of slow and clunky, even when it really isn't. So compilation performance is not the only thing that matters, but it's just one of the many ways in which the build tool adds overhead on top of what is actually a pretty fast and performant underlying Java runtime and toolchain. So next, let's talk about IDE support. Everyone knows that Java has great IDEs. Java is almost the IDE language, from NetBeans and Eclipse back in the day, all the way nowadays you have IntelliJ, which seems the dominant factor, VS Code picking up some market share. And all your Java build tools have IDE support. But I would argue that IDE support in Java build tools is often not as good as you'd expect, given how the IDE support is in the rest of the Java ecosystem. So I'm going to pull this up live for you to see. So over here, I have the build checkout for, what is this? This is the Mockito code base. You all know Mockito. It's a popular unit testing helper library for mocking. And it is built using Gradle. So this is an example build. This is the config for the error-prone submodule of Mockito. And it's just a representative submodule that's similar to all the others. So if you look at this build, it has IDE support. You do have syntax highlighting and so on, and interpolations are highlighted. But if you look at JVM args, for example, let's say you didn't know what this was. If you try to get its documentation, you don't get much. I think you can set it up. I haven't. But if you try and jump to it, you often will get these stubs. So you get a getter and setter, but you don't get anything else. If you pull down the sources, you'll get the documentation as well. There's like a little Java document. But what's actually interesting here is like, what was the value before I set it? And where is the value being used after I have modified it? So if you already memorize what JVM args does and what compiler args does, and you've memorized everything in your Gradle build file, you can probably make things work. Or if you copy paste existing build files and cargo cult them, can probably make things work as well. But this kind of like IDE experience where you jump to a stub is kind of not what you expect from a Java IDE, from a Java IDE as a Java developer. In contrast, if I open up any random file in the Mockito code base, I should be able to look at any of these methods. I should be able to jump to it, find not just the documentation, not just the signature, but also the implementation. Like, what does this method call? What does that method call? Where do these come from, and so on. So even if you don't have documentation, or documentation is out of date, or the thing's so complex and someone overlooked documenting this particular case, in any Java code base, or even other languages like Kotlin or Scala, you can always just navigate around your IDE and find out what's happening. But that's not the case in build tools like Gradle, right? Like you jump to test. You cannot jump to test. Jump to test implementation. You get this dependency handler thing. JVM args is just a getter and setter. Why is that the case? So the reason that's the case is that these JVM arg, compiler args, what they really are is they are global mutable variables. And just because I wrap them in a getter and setter doesn't make them any less global or any less mutable. And if any of you who have used global mutable variables in your application code, you know that if you jump to a global mutable variable, you get its name, you get its signature, maybe you get its Java doc, but you don't get its implementation, where the value came from, where the value is being used, because you don't know. It's a global mutable variable, could be set anywhere, could be read anywhere, and neither you nor your IDE will have an easy time figuring that out. So that's exactly the experience we have here with jumping around our Gradle build. These are basically global mutable variables, and IDEs are not good at that. Whereas in the application code, you try to avoid that, right? In application code, you tend to use classes, methods, overrides, and inheritance, and so on. And that's why IDEs are able to figure out and navigate around your application code in a way they cannot navigate around your build code using Gradle. And in this example, I showed you Gradle Groovy DSL. The Kotlin DSL actually has the same problem, even though it's statically typed, it doesn't really solve this global variable problem. And the Maven DSL, Maven's XML also has a similar problem. It doesn't have variables per se, but you cannot jump around your Maven pom.xml. You can jump and you get your XML schema definition, again with the signature and the documentation comment, but it doesn't tell you what that thing actually does. And if the documentation is insufficient or incomplete or missing, or then you're basically stuck. There's no way for you to figure it out, except you go to ChatGPT or Google or Gemini and hope it can copy paste something from Stack Overflow for you. So that's the idea of IDE support, where even though Java is great with IDEs, the build tools like Maven or Gradle are just not quite up to that standard that you'd hope for. Lastly, let's talk about programmability. So most build tools have a bunch of built-ins. That's great. They'll have plugins as well. You can pull things in off GitHub or Maven Central. But eventually you'll find cases where the built-ins don't do what you want. The plugins don't quite do what you want. Maybe you're doing something very unusual, or maybe the plugin just doesn't quite do it the way you need it to be done. You need to adjust it. And that's the case where you need to customize your build yourself. So as an example customization, I'm going to say, let's save the project line count as a line count.txt resource file for us to use at runtime. So this is a bit contrived and arbitrary, but it's representative of the many arbitrary things any real project has to do. Like Netty, we saw earlier, has to compile C code using GCC or Clang. Mockito has to do bytecode mangling and rename some class files in order to make things work. You may have a custom linter or bill of materials you need to publish and so on. So all of these things are common in real application code bases. And just as a representative sample, let's say we want to save the line count. So this isn't rocket science, but it's surprisingly tricky. So here is an example Maven implementation, and there's a bug in it. And this is using Maven exec plugin for, that's a standard where you exec shell scripts and other things from Maven. It's using SH. It doesn't work on Windows, of course, you all know that, because Windows doesn't come with SH. But apart from not working in Windows, there's another bug. And I'm going to give like 10 seconds, see if anyone can spot it, and maybe leave it in the comments if you spot the bug. So where's the bug in this like Maven exec line count program? I'm going to see my timer. So the bug here is that we forgot to escape our ampersands, because we are not just writing bash, we're not just writing sh shell, we are writing bash embedded in XML, and XML requires you to escape your ampersands with ampersand amp semicolon. So this is the kind of thing that it's not impossible, but given how simple this requirement here is, it becomes really easy to make these mistakes in your build configuration. And this is like the simplest possible requirement you could ever have. Any real world project would be much more complicated than this in what they need to configure, and it becomes correspondingly harder to spot the bugs. There are other solutions other than Maven exec, but they all have their own pros and cons, and none of them are as trivial as you would hope for. Another example, here's the same customization defined using Gradle. So Gradle has a different set of trade-offs. Gradle runs on the JVM, so you don't need to worry about bash or Windows compatibility. But Gradle has a whole bunch of these like depends-ons, input files, output files, calls that all are room for error. Again, there are multiple ways to define Gradle scripts. This is just one of them. Gradle has 4 different DSLs or APIs. But this is kind of representative of what you'll see in the wild. And there is a bug here again. And I'll just wait another 10 seconds, see if anyone can spot the bug. If you do spot it, you can leave it in the comments or chat. So the bug here is that while we were listing source main Java, we were declaring as inputs the source main folder. So this would mean that if you touch source main resources, if you touch source main templates, we will rerun this custom task and recompute it, even though there's nothing changed on this that could affect the output. So the output of the custom task will be the same, it'll be correct, but it'll be non-deterministically slower than it could be depending what files you touched. So this example of programming Maven or Gradle kind of illustrates how difficult these tools are to work with. Like, it's not that it's impossible, but such a simple hello world requirement already has tricky bugs that many senior people will not be able to catch in code review. And that's how these bugs will slip through into your main branch. These bugs will slip through into your third-party plugins. After all, the plugin authors are human too. They'll make the same mistakes and overlook the same things you do. And that's how build systems tend to become slow, flaky, and non-deterministic over time, because this non-deterministic slowdown we see in Gradle and the brokenness on Windows and with ampersands we saw on Maven are going to cause problems in your real projects, either directly or indirectly. So that's the kind of summary of why build tools are hard for users, right? So performance, ID support, and programmability. Java is very good at all of these facets, but the Java build tools like Maven, Gradle are not always so good. So the obvious question then people ask is, well, why doesn't someone just make a better build tool? Like, it's been 20 years since Maven came out, almost 20 years since Gradle came out. Why is it taking so long? Why hasn't it just already been fixed? And I think the answer to that is that build tools are very hard, not just for users, but also for anyone who's trying to implement or design a build tool. So every build tool starts off simple. For example, if you use JBang, that's one of the nice applications, programs you can use to run Java programs from the command line, like single file Java programs. We can declare dependencies, Java version, some other flags, and you can just kick it off from the command line easily. So key value pairs, really simple, really nice. But over time, as your key value pairs grows, it tends to get messy, and you tend to want to put them in some kind of hierarchy like JSON or YAML or TOML in order to keep things neat. An example of this is GitHub Actions, which can be thought of as a build tool of sorts. So GitHub Actions, you can see that we have jobs, we have multiple jobs, each with their own schema, like users and with. Some have needs. There's some other files you can put in to configure it. And even though there's a lot of things, the fact that it's in a YAML tree kind of makes it a bit neater than if it was in a flat list. But when you look at this, you realize that although your GitHub Actions config looks like a YAML tree, it actually identifies in variables. Like message is being passed in here, which is being passed here. Build is defined here and being used here, referenced here. Share.yaml is defined here on the left, imported here on the right. So when you actually think about how your GitHub Actions works, like when there are problems in your GitHub Actions, you're not thinking of the GitHub Actions tree, because a tree is not what matters. A tree just happens to be a convenient format to write what you actually care about, which is a graph. And this is the case for most build tools. Like, you have some syntax, whether TOML or YAML or XML or Groovy or Kotlin, and you are constructing some kind of tree-like data structure. But in the end, you have this graph that you need to build, and the graph is what you care about. What can be parallelized, what cannot, what depends on who. When you change something here, what could potentially break? All that you need to think about the graph. The last thing to mention here is the idea of mexins, or inheritance of some kind. So in Maven, you now have Maven 4, you now have the ability to define multiple inheritance in your POM files. Previously, you could define one parent POM. Now you can have mexins to define multiple parent POMs, where this mexin here references this POM here and pulls it in. And this is obviously necessary in larger builds. You don't want to be copy-pasting the same boilerplate in every subfolder. This results in duplication. This results in maintenance problems where things tend to drift over time. Maybe when you merge up two pull requests, one pull request will add a new POM, the other pull request will update all the old POMs, and now they're out of sync. So obviously you want something to dry it up, just like any other Java application code base. And so you need inheritance of sorts, some way to template your build. So what I'm getting at here is that although people think that build tools just want their build tool to just work, build tools are actually rather complicated pieces of software. They are graph computation engines that need to allow their users, which is the people like you who are writing applications or mono repos or separate poly repos or whatever, libraries, you as a user need to be able to use a build tool to define templated graph computations, such as what we see in the bottom here, where we have 3 modules They each have their own small build graph that look almost the same, but depend on each other and are different in subtle ways. So we need a graph, like we discussed earlier. Like that's how the tool can decide what order in which to run build steps and what you can parallelize and what you cannot. You need to actually compute things because jars and class files don't create themselves. Someone needs to say how they're created, whether it's you writing bash scripts or whether it's some plugin author writing some Java code in some plugin that you pull in. And they need to be templated because the different modules in the build are often extremely similar, but often, just as often, not quite the same. So they have the same overall structure, but some parts will be different. Someone has a custom linter. Someone has a custom post-compile step to process the bytecode. Someone has a custom resource generator. So they need the templating, but you also need some way to customize these templates. So GitHub Actions deals with this with needs keys, that's your graph, bash snippets, that's your computation, and curly braces, which is templating. And some tools may hide this in plugins, but that doesn't actually solve the problem. That just means that rather than you creating bugs in your build, the plugin author will create bugs, and you pull in that plugin, your build is just as buggy as it would have been otherwise. And I'm sure all of you have dealt with buggy plugins that don't play well with each other, or plugins get unmaintained because the build authors have trouble understanding these templated graph computations. And this makes builds complex, right? So if I ask you to define an API, or I have to go define an API to manage templated graph computations, it turns out you have to answer all of these questions, and these questions are not easy to answer. Like if you don't answer them, people won't use a build tool. If a build tool does not have parallelism, who's going to accept using one core out of 10 or 12 on a modern MacBook? If a build tool doesn't have caching, who's going to accept like recomputing the same thing over and over and just wasting time? And if you look at something like the Gradle build we saw earlier, you agree that, okay, yes, it's kind of complex. It's lots of boilerplate and lots of API surface area people can make mistakes in. But all of this API surface area corresponds pretty directly to what the build tool actually needs to care about. Build tool needs to care about dependencies. Build tool needs to care about customizations, data passing, task implementation, ordering, reading, writing to disk. And because build tools need to deal with all this stuff, that's why Gradle needs to deal with all this stuff. It's not because the Gradle guys want to make a very complicated build tool. It's because build tools are complicated, and as Gradle needs to keep up in order to satisfy the requirements that any build tool needs to satisfy. So that's why build tools are hard for implementers, and that's why people just haven't made a better build tool. Like lots of people have tried, lots of them start simple, like JBang right now is relatively simple. But as it grows to satisfy the requirements that any real project needs, it invariably gets very complicated. And that's why things like Maven, Gradle, Bazel, someone said in the comments, all of these are extremely complicated systems that are quite difficult to learn and adopt. Next, we'll talk about one of my open source projects. I mentioned earlier I do a bunch of open source work around the JVM, and one of them is Mill, which attempts to be a better build tool for JVM projects. So Mill is an open source build tool that targets Java's Kotlin and Scala. There's some nice things I'll show you in a moment. And the build file looks something like this. So Mill builds, it's configured using Scala code rather than XML or Kotlin or Groovy like Maven and Gradle are. But hopefully it doesn't look too foreign to you. So package, imports, extends, class, you know what that means. Object is like a singleton object in Kotlin. I think Kotlin also has an object keyword. It just says this object extends that without having to do an anonymous class. And def is a method definition. So just like Kotlin's fun or Java's public static type, a return type, etc. So Mill's not a big popular project. Like there's a few maintainers, few committers, but we do have some companies using it, including people at places like Netflix or Disney who are using Mill internally. So using Mill looks like this from the command line. You say /mill. We use a bootstrap script like Maven W or Gradle W. This foo object has a compile method, so you can say foo.compile, foo.run. This foo object has a test object within it, so it's foo.test. You can foo.assembly and run the assembly later. Standard build tool things. So far, maybe not so interesting yet. Where I think this can be interesting is the advantages that improvements that Mill can demonstrate over existing build tools. As I mentioned earlier, Mill is a much newer project. It hasn't been developed for 20 years like Maven, but it's able to demonstrate some quite interesting features that hopefully you guys would agree are upgrades. Let's talk about performance next. So in order to compare performance between, let's say, Mill and Maven, you need a build or project that's built using both Mill and Maven at the same time. There aren't that many of those. As I said, Mill is relatively young still, and no one's going to maintain 2 build tools in the project just for the heck of it. So we took the liberty and we ported a few projects from other build tools in Mill just to compare. We ported Netty, for example, which is 500,000 lines of code and 50 sub-projects. We ported it to Mill, got all tests passing in Mill as well as Maven. So we know it's quite a realistic representative port. And once we have all this test passing, we can run benchmarks and compare it. For example, the parallel clean compile benchmark is what we saw earlier, where Maven takes about 50 seconds to compile something, and Mill takes much less time. And I can show you this one live. So if I go to my Netty code base, which I have here, and I say /mill clean and /mill wildcard compile. The first time I run this, it might take a bit longer because Mill runs on a JVM, so it has a cold start. But even the first time I run it, it should take much less than 50 seconds. Let's take a look at how long it ends up running for. So first time I run it, it took about 14 seconds. Second time I run it, it should get warmer. So hopefully it'll take a bit less than 14 seconds. Second time I run it, takes about 10 seconds. And if you keep running it, it goes down to about 7 seconds as the project warms up. And this is what you would do in real life, right? Like you will keep running your compile and test and compile and test and package and deploy. So your build tool will get a chance to really warm up super fast compared to what you see in Maven earlier. Other examples to show are things like incremental compilation. So if I go and change one file, let's go and find an example file to change. Sorry, I need to get my Netty code base back on the screen. So let's pick some random file in the common subfolder. Let's say I pick this guy, and let's say I add a comment at the end. Let's say like hello. So if I do mill wildcard.compile, this is not clean. You see that Mill realizes quite quickly it only needs to compile one Java source file. And because this one Java source file doesn't affect other source files within the module or other modules downstream of it, it doesn't need to recompile them and it's able to just compile this source file and exit. On the other hand, if I do Maven, I'm just going to compile everything again. Again, this is without cleaning. You'll see that Maven isn't quite so smart about this incremental compilation, and Maven ends up basically compiling the whole Netty code base. It'll take another few tens of seconds. Just to answer some questions I see in the comments, I have not run benchmarks versus Maven 4. That hasn't come out yet. There are some projects at Lombok. We do have annotation processor support. When you say Maven, I'm using MBNW without the D. The daemon, as far as I know, hasn't been stabilized yet in Maven 3. So I haven't used it. For what I've seen, people don't use it by default, and there's still some open problems. Have you checked with the Maven build cache? No, I also haven't used, this is not using the Mill build cache either. So this is using Mill with a clean compile. So this is apples to apples. Like I did run the Mill clean just now before running the full parallel clean compile benchmark. So like the cleans are clean for both Maven and Mill, and the incremental and no-op are incremental and no-op, both for Maven and Mill. So that's just for Maven. These benchmarks are obviously limited. They are kind of manual. I don't have a huge benchmarking setup and all that. But it just gives you indication of what the potential speed up here is. We did similar benchmarks versus Gradle using Mockito codebase again ported to Mill, and you'll see that the speed up is significantly less than the Maven speed up. Those of you who have ported Maven to Gradle, I know many people have said it's a lot faster, and I believe them. And Mill is just faster still compared to Gradle. Someone mentioned warmed up Mill versus unoptimized Maven build. This is a Maven build for Netty. It's an open source project. These are the instructions I got from the build maintainers for Netty project. And this is the Mill. This is a Mill build that's equivalent to that. I didn't specially optimize the Mill build. I did not specially de-optimize the Maven build. This is a typical build you'll find out in the wild. Maybe you're better than Maven at some people, but not everyone's an expert at optimizing their builds. I guess apart from compilation performance, other things I want to talk about here that are interesting are large code bases and monorepos. So Mill works quite well up to like a few hundred to maybe 1,000 sub projects, which I know that many other build tools like Gradle or SBT, you end up having very long loading and configuration times as a number of sub-projects grows. Often like around 100 sub-projects or Gradle or SBT or Maven build you can start seeing a lot of overhead, even separate from the actual compilation. In Mill, you do have overhead, but with 500 sub-projects, if there's nothing to do, the overhead somewhere around 2 seconds. So there's overhead, but it's not like a blocker, even as your project is very large. And there's support for multiple languages, which is nice in the monorepo. Another interesting thing is a Chrome profile. So the biggest question everyone always asks about the build tool is, why is it taking so long, and are we there yet? Is it done yet? And to answer this, every command you run in Mill generates a Chrome profile, which I can show you. So if I run the Mill clean and Mill wildcard.compile, it takes about 10 seconds. We saw that earlier. But what's interesting is that while it's compiling and when it's done, it generates this /mill Chrome profile file. So this Chrome profile is a format that is not meant to be read yourself, but visually. But you can load it into your browser. Everyone who has a Chrome browser has Chrome tracing on your as a Chrome / tracing built in. I bet all of you didn't know that. And you can use this to visualize these parallel performance profiles that any application load. So if you have your own workflow that you want to visualize, you can also generate this format. This is a very simple JSON format that's documented online. Just search Chrome tracing format. But from Mill's perspective, what's interesting here is basically any command you run, you get a 2D explorable representation of where the time went. There's no like mystery of like, why is my build taking so long? You can see where the build is taking so long. And if you want to do something about it, you can decide to do so. Like you can see where it's fully using all my CPUs at the start, got bottleneck to common compile, got bottleneck to microbench compile at the end. If you want to improve this, even if you know nothing about Netty, know nothing about Mill, you can probably think, hey, maybe I can break up the microbenchmarks, they compile in parallel. That's just an example. Like maybe 10 seconds here is not worth your time to go and optimize. But in any like real world project, I'm sure there are many build workflows and test workflows where you're wondering, where's my time going? And Mill makes it very easy to find out. Now, Maven, Gradle, SBT all have plugins that let you do this, but they're always a bit finicky to set up. And with Mill, you're much more likely to actually open this up, understand the runtime characteristics of your build steps, and take action to improve them than you are with other build tools. Last thing worth mentioning for performance is the idea of selective testing. So Mill has the ability to take a snapshot on your main branch, let you check out your pull request branch, and you can ask Mill, hey, given the code that's changed, what tests now must be run in order to validate them? And any build tool has this information. Any build tool knows what module depends on what module, what test module depends on what other test module, and so on. So any build tool should be able to say, hey, you touch this module, you need to run that module's test and any downstream module's test. But Mill just has this built in, so it's really easy to set up. Whereas if you can do this in theory with Maven or Gradle or SBT or others, but you might have to write your own Python script or find some plugin to do it, and it's always a bit finicky enough that many people will not do so and will just suffer the slow CI times. Whereas in Mill, it's quite easy to set up, so it's very easy to just avoid running all unnecessary tests, which matters a lot on a big code base or monorepo, where most tests will not be relevant to the small folder that you're changing. So that's the performance angle. Again, I'm going to say the benchmarks aren't super rigorous, but at the same time, they're not super biased either. It's not like I purposely went to slow down the Maven build. It's not like I purposely went to sped up the Mill build. It's just kind of representative of what you'll find in the wild. And I think all the other features like the large code base support, the build profiles, and selective testing are also quite interesting and doable, but troublesome to do with other build tools. Next, let's look at ID support. So earlier, we looked at the ID support for the Mockito code base with Gradle. I'm going to pull up the same thing with Mill, and we can compare the two. So over here on the left, I have the build config for the error-prone submodule of Mockito in Mill. And on the right, I have the build config for the error-prone submodule of Mockito in Gradle. First thing you might realize is that they have a lot of the same information. So this module needs these flags, compile time flags, runtime flags, needs these dependencies and test dependencies. And the spelling is a bit different, but it basically, in Mill, you have to configure the same things that you would have to configure in any Gradle, Maven, SBT, or Bazel build. So where things are interesting is where in Gradle, when you jump to something, you typically get a getter and setter. This is covered by the nature of its global mutable variables that you use to configure Gradle. In Mill, rather than using global mutable variables, you'd use overrides like here. So def is a keyword to define a new method in the Scala syntax and Mill uses. It's a sequence of strings, and IntelliJ knows that it's an override. IntelliJ can pull up the documentation of the overridden method, and IntelliJ can let you jump to the implementation that was overridden. You can see the default value here is an empty sequence of strings. The syntax, again, may be a bit foreign because Mill uses Scala syntax rather than Kotlin or Groovy that Gradle does, but hopefully you can more or less guess what's happening. And now that I've jumped to the overridden member method, I can look at forkargs and see where it's used. Forkargs is used in runner. Runner is used in run background task, run fork task, and run fork task is used in run main and run. Here it is. So what's interesting here is that in Mill, when I jump to forkargs, I don't get stuck like you see on the right from Gradle jumping to JVM args. I don't have to go search through the Gradle source code. I don't have to go ask ChatGPT or copy paste some cargo culture config from another project. I can instead navigate around my build graph the same way you would navigate around any application code base using an IDE. So even if documentation is out of date or documentation is wrong, or using some plugin that may not be documented, or you're trying to debug some edge case that documentation doesn't cover because edge cases typically happen rarely, but they do happen. You can always navigate around and find what's going on. I showed you navigating downstream, but you can navigate upstream as well, like final main class, right? Let's say I don't know what that is. How do I find out? I jump to it. There's no documentation. That's bad. But I just have the implementation right here. I can see what it does. It just delegates this other final main class opt. I jump to that. Again, no documentation, but again, it's not a blocker. Like I have the implementation. I can see what it does. I can see that it calls main class. This is any explicitly specified main class. So, and if there is one, I use it. If there's none, I call all local main classes. This is any main classes detected. So it uses this class graph project to scan for public static void main array args of array string methods. If there's exactly one of 0, it raises an error. If there's 1, it returns that. If there's none, it also gives you an error. Again, the syntax may be a bit unfamiliar, but I guess the point here is all of this is exactly what you're doing every day in your application code when you navigate it using an IDE. In application code, it's never as well documented as you can hope, but the documentation being missing is never a blocker for you to understand, explore, and in the end, confidently make changes to your application. With build tools like Maven or Gradle or SPT or others, you're often stuck because of these global mutable variables that block your IDE support. But because Mill is defined using method definitions, method calls, and overrides like we see here, and IntelliJ can see here, IDEs like IntelliJ are very competent at navigating a Mill build graph, so you never get stuck, even if you don't know what's happening. So that's the IDE support angle. I think that's very cool. Like I don't think it'd be an exaggeration to say this is the best IDE support you'll find at any build tool in any programming language. You go to other programming languages like JavaScript with Webpack or Snowpack, like Python with UV. You go to Bazel, you won't find this kind of easy navigation around your build graph that you see here in Mill. So that's the IDE support angle. Lastly, let's talk about programmability. So most build tools require extensions to be published as plugins. And this is good and bad. It's good if there are plugins that let you do your things. It's bad if the plugins don't quite do what you want, or maybe the plugin was last updated 5 years ago on GitHub and it's unmaintained, or the plugin might have security vulnerabilities because no one really pays attention to plugins as much as they do the actual application code. So Mill is different in that although Mill does have plugins, which you can use, if you can't find the plugin or the plugin doesn't quite do what you want, you can always just write code to do it yourself. And let me show you what that means live. So, okay, I have a bunch of IDEs open. Let's find the right one. Hopefully all these demos work. So over here, I have the example IDE, example Mill build for the Hello World Java project. As you see, there's nothing in it. It basically says object foo extends Java module. That means that the foo subfolder has a Java source code in it. And I'm just using all the defaults. So default source folder, default resource folder, default compilation, everything just default. So Mill follows Maven's convention over configuration. If there's nothing to configure, then there's nothing to configure. So what if I don't want the defaults? What if I want to count the lines of code in this project and add it as a line count.txt file? In Mill, custom tasks are methods using Mill Scala syntax. Methods are defined using def. So the def line count equals, maybe it's a task. And within this method, I can call out a task. For example, I can call foo.one of the source tasks. You're not sure which task to call, you can ask IntelliJ. In this case, I probably want all source files, which is all individual source files fed into the Java compiler. I can then map that to every file. I want the file path, read lines using the helper this helper library that Mill comes bundled with, size, and sum them up. And this is all you need to do to define a custom task using Mill. So if I do Mill show foo.line count, you see this example project has 17 lines of code in it. That's over here. If I do Mill inspect foo.line count, you'll see that we capture things like the Java doc for you, the dependencies for you, so you don't need to say depends on. We capture that file name, line number, method name for you, so you don't need to put those in strings. Just all these obvious things that you already wrote and we know what you mean, we just take it for you. So that's all you need to do to define a line count task. But we haven't yet integrated it into resources. So to do that, resources like line count are just a method. And in Mill, the way you customize methods, like in any other OO language, is you override them. So I do override def resources. Again, you're not sure which one to override. You can ask IntelliJ. In this case, I want normal resources. I call the super. And I'm going to write to this task.dest folder, which I'll explain in a moment. I'm going to write my line count as a string. And I'm going to append, so this syntax is the Scala syntax for append, a reference to the task.dest folder. So the syntax may be a bit foreign again, but hopefully you can more or less guess what this stuff means. But what's this task.dest folder? So if I go to the terminal and do Mill show foo.resources, you'll see that apart from my normal foo resources, which is the super resources that we have overridden but kept around, we have out foo resources.dest, which is task.dest. So why we have this task.dest is that the file system in any build tool is the world's biggest global mutable variable. Anyone can read from it, anyone can write from it. There's no types, there's no schema. You don't know who's reading what or writing what. Your plugins will collide and stomp over each other's files. You don't know if you're cleaning, whether you're cleaning something you didn't want to clean. It's generally a big mess. So to solve that, or at least mitigate it, Mill says that every task gets its own local mutable file system that it can write to, and other tasks can only read from it. So foo.resources gets out/foo/resources.dest, and foo.compile will get the compile.dest, and assembly.dest. Different modules will have a different module folder. And by doing this, it turns the global mutable file system into a locally mutable but globally immutable, like files on disk, and really helps avoid a lot of the problems that dealing with files gives you in other build tools. And now if you do Mill foo.run, you'll see that our application code is able to load our line count from disk and provide it at runtime. So let's take this one step further. Let's say I wanted to use a third-party library in my build system, and there's no plugin for it. Let's say I want to render my line count as HTML, and maybe I want to use like ThymeLeaf. So Mill doesn't have ThymeLeaf support built in. It's a build tool, not a web framework. And if you try to use this from the command line, it'll yell at you, just like my IDE here is yelling at me up here. So, but what Mill does let you do is let you really easily depend on things in your build. For example, I can say, similar to the JBang syntax we saw earlier, I can put a YAML command here that says my Maven dependencies include org.thymeleaf, :thymeleaf, :3.1.1.release. So now, if I reload my build and in the IDE, and the IntelliJ gods are smiling at me today because sometimes IntelliJ can be a bit flaky, you see that now it's not complaining about ThymeLeaf anymore. I can see ThymeLeaf in my libraries list, and I can start using ThymeLeaf with full autocomplete, with full like IntelliJ assistance and so on. I want template engine probably here. So now I can say, for example, I'm defining a new task HTML snippet equals task. I'm going to call var context equals new context. This is just using the ThymeLeaf API directly. Context.set variable line count to line count. And then new template engine dot process. I think that's API. Sorry, I forgot I imported the wrong thing. So template engine here. So now I can look at the docs. And then I'm going to copy the template from the slides because time-leaf syntax can be a bit finicky. I'm just going to copy this over. And I'm going to put my context here. Now, if I do mil show foo.html snippet, you'll see my string. If I open up the file on disk, you'll see in out/foo/html snippet.json, you'll see that I have my cached value JSON serialized with some metadata, so mil knows when to invalidate things for you. And if I do mil foo.run, you'll see I'm able to use the HTML at runtime. I'm not doing that yet because I need to swap out this line count with HTML snippet. Okay, now you can see that foo is able to use my build HTML that I built using a third-party library at runtime in my application. In this case, a very simple like hello world echo application. So no one actually wants to render HTML containing a line count into a resource file at runtime. But what's interesting here is that this is kind of representative of the many things that people do want to do. People do want to use third-party libraries in their build to do things. These are often libraries you use in your application code as well. People often do want to customize your build in ways that maybe plugins that are available don't quite satisfy your need. And in Mil, it just is very easy to do so. It's just very normal object-oriented code. You have objects, you have classes, you have method calls, override, and super. So although the syntax may be a bit foreign because Mil uses Scala rather than Kotlin, hopefully the concepts here are concepts you're already familiar with. And when I said override def resources called super, you immediately know what that means. I don't need to teach you the concept of how I'm customizing this resource task. You know what super means, you know what override means, and we're done. And when you look at this, there is no Mil time-leaf plugin. There is no Mil line count plugin or Mil HTML rendering plugin. You can just customize it yourself because as JVM, Java developers, Kotlin developers, or some of you may even be Scala developers occasionally, all of this should come second nature. Var context equals new context, call the API to do things. You don't need a plugin to customize your code when your build can be customized with very simple ID supported code. So that's the programmability angle, which I think Mil is very cool. And I think compared to what we saw earlier with Maven and Gradle, it's much less error prone. Like you get much better ID support, much better compile errors, and there's much fewer things that you can get wrong in your Mil, customizing your Mil build than, for example, Gradle we saw earlier. So that's Mil as a better Java build tool. Hopefully some of you believe some of the things that I said are nice. I know not everyone thinks the benchmarks are nice, or maybe not everyone's familiar with Scala syntax. But hopefully overall, I think this is quite interesting. Hopefully you guys agree. And the obvious question is, if Mil can do this, why doesn't everyone else just do it? Why doesn't Maven or Gradle just make it super easy to program, have super good ID support? And I think the answer to that comes in that Mil is built around this concept of object-oriented builds, which is what allows all these user-facing benefits to take place. But without it, it's very difficult to get these benefits, improvements. So earlier we talked about templated graph computations. They're complicated. You can use YAML, you can use Groovy, you can use Kotlin, you can use XML. It's still going to be complicated. Everyone has to do it, and it still will be complicated. Maybe your plugins do it, but that just means your plugin authors will have bugs rather than you having bugs. That doesn't really solve it. And Mil solves this by modeling templated graphs using object-oriented programming. It turns out that object-oriented programming is a perfect fit for templating graph computations. And you all know object-oriented programming already. So when we saw earlier, object foo extends Java module. This is literally a JVM object extending a JVM class. And when you extend the class, you get these methods, and the methods call each other like so. This is somewhat simplified, but you get the idea. Compile gets used in class path gets used in assembly together with resources. So because it's just object-oriented programming, when I say def line count calls all source files and map and read line size sum, and when I say override def resources calls super resources and also calls line count, I don't need to teach you anything for you to know how this affects my build graph structure, because you know what method defs do, you know what method calls do, you know what override and super do, you know this. And if I want to template this build graph, I just make my foo module into a class, or in Mil it's called a trait, and I extend it in multiple objects. So by extending my same class in multiple objects, I have templated my graph. So even though you don't need to learn anything, you already know how to template graphs using computations using MIL. And once you've templated these graphs, MIL can then pick them up and do the rest. So for example, MIL can look at the graph and say, hey, compile and line count can run in parallel because they don't depend on each other in the graph. MIL can look at the graph and objects and say, hey, every task has a fully qualified name, the object name followed by that method name. So we can use that to assign them unique locations on disk for their JSON metadata and for the file folder to put their file outputs for tasks like compile and assembly that have file outputs. And we can guarantee that they will never collide because every method in JVM is guaranteed to have a unique name, ignoring overloading and some other trickiness that we are going to skim over. MIL can automatically invalidate things for you. For example, if you touch the resource folder, which is now super resources, MIL just does a breadth-first search, sees that these two guys need to invalidate. MIL knows that compile and line count do not need to be invalidated because they are not downstream of our exchange. MIL knows where to fetch the data that was cached earlier for compile and line count because they're at a standard location. And MIL knows where to delete the data that was cached earlier for assembly, again, because it's at a standard location. And MIL can do all of this with no code in your build related to dependency tracking, parallelism, or caching. You don't see any depends on calls. You don't see any file input declarations, file output declarations. You don't see threads or locks or futures or executors. You don't see cache key computations or cache reads and cache writes and cache invalidation. You as a plugin author or you as a build author, like writing build for your own project, you just write very vanilla object-oriented code with objects, classes, methods, calls, and overrides. And MIL will handle the build stuff for you. So we saw earlier why are build tools complex, and we said Gradle is complex because its complex API represents the complexity of the build tool. MIL also needs to kind of handle all these requirements, but MIL manages to squeeze all of it into a much smaller, much more familiar package. So the CLI name for a task is not a string, it's just a method name. Your own custom tasks are not some weird registration callback pattern, it's just a method. Like what needs to run in what order is just a method call order. And what task depends on what is also a method call order, and how task pass data is also through method calls and return values. So MIL does not skimp on the complexity, but MIL manages to package it in a way that's much more familiar to anyone who's learned Java 101 20 years ago in high school or college. So half of these questions can be answered basically by methods calling methods give you a graph, and the other half can be answered by like objects and classes are useful, so we can use them to template our methods and customize and override them. All of these are very familiar concepts to anyone who's learned Java in school. So that's the idea of object-oriented builds. MIL builds are methods, objects, and classes. So all the same keywords work, same semantics as you know, same semantics as your IDE knows. That's why your IDEs are intelligent, able to navigate the MIL build so effectively like we saw earlier. MIL handles all the other build stuff for you 99% of the time. So there are ways for you to customize it, but usually you don't need to. This means you get good performance because you don't have plugins forgetting to cache things, and you don't have plugins forgetting to turn on parallelism. It means you don't need to clean because you don't have plugins screwing up the cache key computations or the dependency registration and causing the things to run in the wrong order. And it just makes life easier for everyone, like you as a build maintainer and you plugin authors, and me as a MIL maintainer who maintains the tool itself. And that means you have time left over to do other fun things like selective testing or Chrome profile integration or tooling integrations. And for you, it'll be more time spent on your application code. But talking about tooling integrations, as you saw, MIL is quite easy to extend and integrate with tools. I've integrated Timeleaf in a few lines of code quite using its Java API. And we have taken the liberty of just integrating most of the common tools you'll find in Java, Kotlin, and Scala open source ecosystems. Not all of them, but all the linters that I found, all the formatters, the code coverage tools, the test frameworks, some of the web frameworks as well. And if there's something that's not on this list that you want to use, it shouldn't be too hard for you to integrate it yourself, as we saw earlier. And if you like your integration and want other people to use it, you can just publish your integration in Maven Central, and people can depend on it just like we depended on Timeleaf earlier. So that's the last idea of object-oriented builds, and that's what I think is really cool about MIL. Like, there's so much complexity in these templated graph computations, but MIL is able to package the complexity in a way that's so familiar, you don't even think about it. Like, you don't even think when you use extends or override or super, and how you use method calls. All of this is second nature, And that's why Mill is able to provide these improvements, I think, where other build tools like Maven or Gradle have struggled over the last 20 years. This is the last slide. I won't read it out to you. It basically summarizes everything we saw earlier. I guess the long and short of it is, hopefully you found it interesting. Hopefully some of the things I showed you that Mill can do that Maven or Gradle can't do. Hopefully you find some of those valuable, and hopefully you believe some of the benchmarks or some of the demos. All of this was done live. I didn't fake anything. And most of the code is available on the Mill website in the example builds for Netty and example builds for Mockito and other projects, if you want to go try it out yourself. So the documentation's here. There's examples, there's documentation sections for Java, Scala, and Kotlin. So if you use any of these languages, you can use Mill, any version of Java, any version of Scala. Kotlin, I think we only support Kotlin 1.9 and 2. We don't support earlier Kotlins. There's some experimental Android support here. And if you're migrating existing code base, someone asked in the chat, there's migration instructions along with some automated migration tools. So you can't automatically migrate all projects from Maven to Mill, but we do a best effort trying to get all your Maven dependencies lined up, your Java version and flags lined up. And you might have to fix the rest, but it's less work than doing it yourself from first principles. So I think that's the end of the presentation. I hope everyone enjoyed this, and I guess I can now take questions. Thanks for listening.
Thank you so much. I really appreciate that presentation. I love hearing about how people go out and solve problems that they're facing, like you'd faced with other build tools, by creating open source projects like this. And it was really interesting to see the live demos. That is always risky. You got to pray to the demo gods that nothing's going to go wrong, but I thought they were great today. And yeah, it was wonderful to see those comparisons as well. So we do have a few questions in the chat. I'm going to send them your way. So I'm going to start with one by Simon. Thank you for your questions. I saw you had multiple in the chat. I know Hawaii's already sort of covered some of them, but we had this question that I don't think was covered, which is, how swift is the compatibility of Mill with new Java versions? Because things like Gradle tended to lag a bit.
Honestly, I don't know. Most of the people who use Mill haven't been super up to date with the latest Java versions. I think generally we should support new major versions within like a few weeks. But Java hasn't released enough new versions in the last few years for me to really give you an actual benchmark. But at least like right now, we support up to Java 24, which I think is the latest one. I don't think Java 25 is out yet. When Java 25 comes out next week or next month, then we can go and add support to it.
Cool. That's fair enough.
Cool.
Simon, hopefully that's answered your question. Please let us know in the chat if that hasn't. But hopefully, as Howie says, we'll look forward to Java 25 when it comes. Perfect. Thank you very much for your question, Simon. I'll move on to one by Stefano. Thank you, Stefano, for asking a question. So Stefano's asking, does using something that is not in a task from something that is make Mill lose track of dependencies? So if yes, are there safeguards against misusing the API?
Okay, this is a very interesting question that I won't have time to go into too much detail, but you can depend on things, for example, var x equals 1, 2, 3 outside of a task and use it within a task. For example, maybe I want to include it in my line count string. When you do this, we do not have a task graph anymore because x is not part of a task. Or if I do like def y equals 4, 5, 6 and append that as well, x and y are not part of tasks. So what Mill does in this case is that Mill will read the bytecode of all of these compile build files. Mill is written in Scala syntax and compiles to Java bytecode like any other bytecode. We will take the bytecode. We will do a breadth-first search on the bytecode starting from all these methods, and we will kind of detect that HTML snippet depends on y and the method y, and HTML snippet depends on the field x, which is set in the constructor of foo. So there are some limitations to this. We cannot detect reflection because reflection usually doesn't show up in the bytecode. We cannot, sometimes if there are abstract methods or virtual methods, we have to be conservative and it may invalidate more things than it needs to. But generally, it's able to keep track of things even outside of your tasks with the caveats I mentioned earlier. So it's not as precise as within tasks. It will not be as parallel as within tasks. There will be some invalidation because Mill is not sure like which implementation of virtual method delegates to, or which constructor. Mill just knows that this method, this field was set in the constructor, but doesn't know when you change the constructor, which bytecode is actually changing that field. So there will be some loss of precision, but generally it should still work. Just perhaps a bit slower as Mill recompiles things it doesn't need to.
All right, awesome. Stefano, great question. I loved how in-depth that was. So thank you very much for asking that. Hopefully that's answered your question. Let us know in the chat if it's not. I will move on to another question here by Johan. Thank you very much for asking all these questions. It's great to get so much interaction with you. So Johan's asking, is there a Maven to Mill migration guide or tooling? I think you showed a bit of a guide earlier, but you said it wasn't like completely everything, or?
Yeah, so there is a guide. So basically there are a few steps. The basic strategy for migration is you do not want to break the existing build tool. And Mill allows you to do that. Mill allows you to leave all your source files and resource files and stuff in place while you're setting up Mill build for it. We did that for the Mockito and Netty builds you saw earlier. So you leave all your source code in place. You set up your Mill build, and you get your Mill build working. Keep both for a while, and then after you're 100% happy with the new Mill build, then you delete the old one. So this is a very conservative way of migrating, but this is something I've done many times before, from Maven to SPT, or SPT to Bazel, or Bazel to a new version of Bazel, or Pants, or whatever. So in more detail, there is a project importer that does a best effort import that helps you with step 2 here. So at least things like getting all your internal dependencies and external dependencies listed properly, getting a publishing metadata for Maven Central listed properly. Mill will help you export your Maven or Gradle or SPT build. Mill cannot do customization, cannot automatically import customization. So like Mill won't be able to translate the Maven exec bash script we saw earlier to a Mill like Scala function to run in memory in the JVM. Mill cannot do that. So after you run Mill init, most projects, not all, but most will need some manual work to port the last few tweaks of Maven or Gradle or SPT specific customizations that Mill cannot handle automatically. Yeah, so but otherwise it's relatively straightforward. Like the Netty port before Mill init took me about 2 days. Mockito took me about 2 days. For these are quite substantial decade-old projects with non-trivial build systems, including compiling C sources and other stuff. So it's not impossible, but it can take some time. Yeah.
Great. Thanks for the answer. Johan, great question. Thank you very much. Okay, I think we have time for one last question. So I'm going to go to Bruce's question here. So you've talked about how Maven, Gradle, and SPT compared to Mill. How does, it says Annie in this, but he's done another comment that says Ant. So how does Ant compare? Yeah.
Yeah. I guess the way to think about it is Ant lacks a lot of the, Ant gives you ability to write code to do things. Ant lacks all the build tool stuff that you always end up wanting in your build tool. So Ant will not do parallelization for you, Ant will not do caching for you, Ant will not do automatic invalidation or selective testing, or provide you like performance profiles. I don't think Ant has a good way to template your Ant tasks, but maybe I'm out of date. Last time I touched Ant was 14 years ago. So I don't think Ant, so basically Ant gives you the execution layer. The execution layer is kind of a bit of a weird XML bash script. So you won't get as good ID support in your Ant scripts as you would in your Mill tasks. Like you saw earlier, your Mill tasks have full autocomplete, pop-up documentation, and all that. But in Mill, and just lacks all the other build tool stuff. And I think that's why Maven got popular, right? Maven does do parallelization to some degree, caching to some degree, templating to some degree with parent POMs and now with mixins. And so Maven has all the defaults built in, which is very nice. Mill kind of gives you the nice parts for Ant, which is the programmability, but it's all the nice parts about Maven and all the nice parts about just Java and JVM with things like the IDE support and cross-platform support.
Great. Thanks very much for the answer. And thank you, Bruce, for your question. All right. So hopefully I've covered most people's questions in the chat, or Howie covered them during his presentation. Thanks for that interaction. So that's all the questions we're going to have time for today. But that doesn't mean you can't still ask them. Please continue to keep asking your questions in the Slack channel, and we'll try and get those answered for you. And it's also a great opportunity to engage more in this virtual Java community. So do join that. A huge thanks to Haoyi. It was a fantastic presentation today. I loved being able to watch it and being the host for this month's VJug session. So thank you so much to everyone who joined, and thank you to Haoyi again for such a great session.
And thank you to both of you for such an amazing session. I'll echo Grace's comments on that live demo. I've seen live things, and then I've seen that, and that was out of this world. So thank you so much, both Haoyi and Grace, for the amazing session. We'll do a virtual round of applause. I think we've got some comments in the chat already about how much everyone enjoyed it. So thank you to the both of you. Awesome, thank you so much. Well, I'm going to say goodbye to Grace and Haoyi for a second, but thank you everyone for watching. If you've enjoyed this session, as I said, you can join the Slack community. We'd love to see you there chatting, asking questions. If you would like us to have any specific speakers on stage, let us know as well. You can find us on Twitter and X and Blue Sky and all the places, as well as Slack. We like to put together this community for you. And so if there's a speaker, if there's a talk, if there's a topic you want to see, just let us know and we will try to find it. And again, that is the URL to our Slack community. Also, as I mentioned at the start of this, we are raffling off a free ticket to Dev2 Next. So if you really want to go to Colorado Springs or you're located close by, we have a free ticket to raffle off, no strings attached. Also, if you put your information in that form, that's all it does. We don't use your info for anything else or put you on mailing lists or sell your data or any funny things like that. So please register if you would like to win a ticket, and we'll get that to you on Friday. But before I go, if you've enjoyed today, we have another session on the 23rd of September. Alina, who is a developer advocate for Gradle VM at Oracle Labs, is going to be doing a session, and she's going to be joined. What is the session on? It is on Gradle VM JDK 25, new features and practical tips. And she'll be joined by Andres, an amazing human being and Java champion, as our host. So if you want to head over to the meetup page, you can see all the information there. But other than this, one last question in the chat was, will this be recorded? Yes, it will be live on YouTube right this second, so you can rewatch it, share it with your colleagues, share it with your family, have a viewing party tonight, eat some popcorn. But I hope you all enjoyed that, and we will see you next time. Thank you again to Grace and Haoyi for this amazing session, and see you on the 23rd of September. Bye for now. Do, 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 do.